So in this video, I'm going to explain about the decreasing operation, decreasing a key operation in binomial heap, and then I will explain the deletion method in a binomial heap. So name is saying that decreasing the key. It means that I am going to decrease some key value. So whatever the key is that, we know that the binomial heap is nothing but a set of binomial tree, and binomial tree is nothing but a set of node, and every node is having some value, right? So that value I am going to decrease here, and here I am working on the mean binomial heap. Mean binomial heap, it means that parents should be less than equal to their children. So if this property is going to follow, then only we can say that a valid binomial heap. So name is saying that decreasing. So now I'm going to decrease the value. So after decreasing the value, might be this happen that this is not going to this is violate the property of the mean heap. So here if you observe this sentence, a statement I have given, that once the value of the key is decreased, it might be a smaller than its parent key, and that result violation of the mean heap property. If such case occur after the decreasing the key, then exchange the element with their parent. So what we will going to do, if it is violate the property of the mean heap, then we will going to perform swapping with their parent value. So this is going to not violate the mean heap property, right? So here given that the decrease value is saying that 45 is going to decrease with 7. So I'm assuming that here I know that where 45. Here I am assuming that I know the key is 45 key where in the binomial heap. So here is the 45, and this is decrease with 7. 45 is decreased with 7, and now if you check that, is it still valid binomial heap? Valid binomial heap means that is it following all the property of binomial heap, right? So look at that. If this first property is that, is it following the mean heap property or not? So for this reason only, if you check that, is seventh parent is less than equal to, no, condition fail. It means that this is violating the binomial heap property. So for that situation, what we will going to do? So here just now what he said that if it is violate the mean heap property, we will going to swap with their parent. So we will going to swap the value with the parent. So now we will check that is 30 less than equal to, is 30 less than equal to 7. No, condition fail. Then what we will going to do? We will going to perform swapping. So 30 will come down and 7 will goes up. Same procedure for this one also. Is 7 parent, the 7 parent is now 8. 7 parent is now 8. Is 8 less than 7? Is 8 less than 7? Again condition fail. Then what we have to do? We will perform swapping. 8 will come down and 7 will goes up. Now again we will check here. Is 6 less than equal to 7? Is 6 less than equal to 7? Condition true. Then we have to stop here. We will stop here because now it is valid binomial heap. It is valid binomial heap because it's following the mean heap property, as well as their order of the all binomial tree is in increasing order. All this in increasing order. So this is the valid binomial heap. Now I will explain you that all these steps that I have done here in a clear graph. So this one is that I have just decreased 45 with the 7. So 45 removed with 7. Now I am checking that 7 with their parent. Parent is 30. Is 30 less than 7? Condition is fail. Then what we will doing that 30 will come down and 7 will goes up. So this is the graph is here. I have just swapped, and after the swapping I got this one. Remaining part is same. I am not changing with anything in remaining part. I am just working with this 7 and 30. Now this is swapped, and after getting this 7 is come here. Again, now I will check that 7 parent is 8. Is 8 less than 7? Again condition is violating. Again mean heap property is violating. Then again perform swapping, and after swapping I will get it here, right? So I am working here is what? I am working in this path only. I am just working in this path only, right? So this path height, suppose path time complexity, if you check that now, the time complexity, then it will going to take how much? The height of the tree. This is nothing but a height of the tree, and the height of the binomial tree, and any tree, the time complexity is order of log n, right? So here that you are checking with the 6. You are checking with the 6. Is 6 less than 7? Yes, condition true. Then you have to stop, and after the stopping you will get it this one. This is the final binomial heap, and this is the valid binomial heap. This is the valid binomial heap, right? But one more thing is that what will be the time complexity while decreasing the key, and afterward if it is violating the property of the binomial heap, we were maintaining it. For that procedure, what is the time complexity? So here I have just 45 I have reduced with the 7, 45 I have decreased with the 7, and I have done some procedure to maintain the binomial heap property. And in that, what we were doing, we were just performing swapping with their parent, and that is nothing but in that proper path, and that path is nothing but a height, and height, we know that the height is order of log n. So the time complexity of the decreasing a key, the time complexity of a decreasing a key operation, that will take order of log base 2n. This is the time complexity. Now I'm going to explain about the deletion method in a binomial heap. Means I'm going to delete the node. So it's almost similar like a decreasing the key. So that's why I have explained first decreasing the key, and so can you easily understand. So in decreasing the key, we were giving some particular value. We were going to decreasing the some particular value, right? So here in the deletion operation, what we were going to do, we were going to decrease with the minus infinity value. Here we were decreasing with the minus infinity value, but in the decreasing key, what we were doing, we were giving with some value, right? So suppose here if I am going to delete 41, suppose here I am going to delete 41. Here also I am assuming that I know that the 41 where it is, what is the index of the 41, because suppose this is stored in the memory, there it is going to store on the basis of the index and some address, right? So suppose I know the address of the 41 where 41 is stored. Suppose if we don't know the address, then it will going to, first we have to search where 41 is available. So searching will take order of n time, right? So suppose we don't know, if we don't know where 41, then we have to search, and then after we will delete it. First search and then delete. So that will going to take time complexity is order of n. Searching will take order of n, right? And we'll see that deletion, how much deletion operation will take. So just now I have decreased key, I have explained, and their time complexity also I have explained. So same thing, I am going to first I will explain how to delete, then later I will explain the time complexity. So in the deletion operation, first what it is saying that whatever the number you want to delete, whatever the node and whatever the value you want to delete it, that number is going to decrease with the minus infinity. And then after, if we decrease with that minus infinity, that's the very small value, and working on the mean heap binomial heap, it means that again it's violating the property, again it's going to violate the mean heap property, and that mean heap property is followed by the binomial heap. It means that's violating the binomial heap property. So then what we will going to do, again we will going to check with their parent, and when we have to stop if it is going to follow the mean heap property, right? So here I am going to delete the 41. So 41 is going to replace with minus infinity, and if it is going to decrease with minus infinity, it is going to violate the binomial heap property. Then what we will going to do, we have to check with their parent, is 28 is lesser than minus infinity. Yes, sorry, fail. This condition is fail, means 28 is greater than minus infinity, but mean heap is saying that parents would be less than equal to, so condition fail. Then what we will going to do, we will going to perform swapping. So after the swapping, you will get it like that, minus infinity will come here and 28 will come there. 28 will come there and minus infinity will come there. Then after, again you have to check minus infinity with their parent. Their parent is 15. Is 15 is lesser than minus infinity? No, condition fail. Then 15 come down and minus infinity come up. Minus infinity come up. And we were always deleting the root node. Because of that reason, I have just doing this procedure. And after reaching the minus infinity at root level, then we will delete the minus infinity. So if you observe here, then same thing I have done that here, minus infinity came here, and after that minus infinity check with the 15, so again failed, so minus infinity come here. Right, now there is no parent, so minus infinity is there. Now I am going to delete this minus infinity. So now I am going to delete this minus infinity. So I have already explained about this one, that extracting the mean. So that I have explained in the previous video. So if you watch that video, you can easily understand that how to delete the minimum, and then after how you perform that. So here minus infinity reached there, then I am going to delete this minus infinity. So if I am going to delete this minus infinity, what happened, that this connectivity is also deleted. This connectivity is also deleted, right? So what you will get, that you will get the two binomial heap. You will get the two binomial heap. One is that B0, and that is 12 with the B1 and that's 7 and 25, right? Another is that this is a one binomial heap. It will form one binomial heap. Another will form that what, 15 with 28, and another is 33, right? So this is not a valid binomial heap. This is not a valid binomial heap. So for first we have to arrange this. First I have to arrange this one. First I will going to arrange this one, and then after I will perform what, union operation. I will perform union operation here, right? So I will perform union operation. So what we will going to do? First I have arranged. After this arranging, I will get it like a 33, and then after I will get that 15 and 25. This is become the another binomial heap. This is a 33. This is become one binomial heap. This is another one. So for performing union, what it is saying, that first step is saying that we have to simply merge. First I have to simply merge. Second step is saying that if two binomial tree is having same degree, then we perform what? First we have simply merged. So I have simply merged here. Then after it's saying that you have to merge the two same degree binomial tree. So there is a two binomial tree is here with degree same, then I have performed merging. So after the merging, we'll get it. And merging, how you merge that? Merging is how you merge that, because it's working on the min heap binomial property. It means that whatever this binomial tree's node key value is minimum, that will become the parent, and the maximum will become the leftmost children. So 12 become the parent and 30 become the leftmost children, right? So that this is the second step is saying the same degree of a binomial tree is going to merge. But sometimes what happen, after the merging we got that what, three binomial tree with the same degree. If we got three binomial tree with the same degree, in that situation we will going to merge the rightmost two binomial tree. We will going to merge the rightmost two binomial tree. So here I am going to merge these two. Here I will change the color for the better understanding. I am going to merge here is that, here I am going to merge here the rightmost two binomial tree. This one I am going to merge. This two is I am going to merge, and we'll see what will be the output. So I have merged that one, and I have checked that the 7 and 25 was the lesser value. We have checked the root value, and whatever the minimum one, that become the parent, and the maximum one is become the leftmost children. So maximum one is become the leftmost children. So this is their order also changed. This is B2 now, and this is B1 now, and this is the final binomial heap after the deletion of 41. Now we'll see the time complexity of a deletion method. So for the deletion method, the time complexity of what will be the time complexity? So for deleting the node, what we were doing, what are the operations we have used parallelly? We have used here. So time complexity of the deletion operation is that, suppose I have already know that the index of the 41, because here I am performing the deletion of the 41. So I have already know that where 41, what is the index, because here I am not performing searching. If we perform the searching and then after perform deletion method or the decreasing method, the time complexity will be order of n. So here I am assuming that I know that 41 where is stored. I am not performing searching. I am directly performing the deletion method. Then what will be the time complexity? So what are the operation we were parallelly doing? So first we were performing the decrease key. First we were performing decrease key, and I have already explained that the time complexity of the decrease key is order of log n, and after the decreasing I am deleting the element. After the decrease key I am deleting the element, and after the deletion we were getting that the unarranged binomial heap. So I am arranging that. That's also taking time complexity is order of log n. And afterward what we were doing, I am performing that union operation. After performing union operation, so total time complexity of the deletion method in a binomial heap is order of log n. Order of log n. And if we go, suppose if we don't know 41 where 41 is stored, and then we perform here searching also. If we perform searching also, so then time complexity will be order of n. So total time is order of n. If we perform searching only, then if we search the element, then the time complexity is order of n. If we don't search, only perform deletion method, the time complexity will be order of n. Order of log n. So this is all about the decrease key operation, and another is the deletion operation in a binomial heap. Thank you for watching my video.